Hi everyone, this is Jennifer and this is my PowerPoint on bones. So as we have learned, there are many types of cells that create the formation of bones. Osteoblasts, which do not divide, synthesize and secrete collagen matrix and calcium salts. And as the secreted matrix surrounding the osteoblast calcifies, the osteoblast becomes trapped within it. And as a result, it changes in structure and becomes an osteocyte. Osteocytes maintain the mineral concentration of the matrix via the secretion of enzymes. Like osteoblasts, osteocytes lack mitotic activity. They can communicate with each other and receive nutrients via long cytoplasmic processes that extend through the canaliculi or canaliculi. Osteogenic cells are undifferentiated with high mitotic activity, and they are the only bone cells that divide. Immature osteogenic cells are found in the deep layers of the periosteum and the marrow. They differentiate and develop into osteoblasts. The dynamic nature of bone means that new tissue is constantly formed, and old, injured, or unnecessary bone is dissolved for repair or for calcium release. The cell responsible for bone resorption or breakdown is the osteoclast. They are found on bone surfaces. They're multinucleated and originate from monocytes and macrophages, two types of white blood cells, not from osteogenic cells. So there's some other pictures on the right there of the bone anatomy. You can see the innervation inside the bone. And here is another picture. You probably are already familiar with it. There are layers. There's the periosteum, the endosteum, the medullary cavity. I can't even talk. I'm so tired. And then, of course, there's the compact bone and spongy bone. So, yeah, let's go on. There's different types of bone growth. There's intramembranous ossification and endochondral ossification. And additionally, there's appositional growth, where more strain and torque are placed on the bone. It becomes thicker. And what happens if a bone is damaged? Well, the first thing that would happen is a hematoma is formed immediately after a fracture, and that clot stabilizes the broken bone ends and provides the framework for new tissue growth. There's inflammation and, of course, pain, causing the area to become swollen and painful and warm to touch. And in this phase, white blood cells arrive at the injury site to clear away dead tissue and help fight infection. So some inflammation is really necessary. Extensive inflammation can be really damaging. It can build up scar tissue. The next thing that would happen is soft and hard callus formation would occur. And fibroblasts and osteoblasts begin to arrive and create a soft callus or fibrocartilage and collagen to bridge the gap between the broken bone ends. Then there's always around this time possibility of bone infection, osteomyelitis, and it's pretty serious, and it can spread to other parts of the body through the bloodstream, causing you to become septic. Symptoms would, of course, include fever, pain, and even pus-filled drainage. And then long-term bone remodeling happens, and that's the final stage of bone healing, and it can continue for several years after initial injury. And during this process, the hard callus is reshaped to more closely resemble the original bone structure. And the osteoclasts the bone resorbing cells remove excess bone tissue, while osteoblasts continue to lay down new bone, making the repaired bone strong and functional again. Okay, fun fact. The xiphoid process, which is at the very bottom of the sternum, which is below the manubrium and the mediastinum area. The xiphoid comes from the Greek word xiphos, meaning sword, and it's named for its pointed sword-like shape, and the sword tip is at the end of your sternum. There you can see it. And it starts as cartilage. So some things start with a cartilage formation, like in the embryonic or fetus stage, and then ossification is layered on top of it. And with this particular bone, it can take up to 40 years and sometimes never fully ossify. It's small, but it's structurally important. And one of the things that it does is it helps support the diaphragm as an attachment point. And it can, ideally it's just looks like that, but it has been presented in really odd shapes. Forked, elongated, rounded, reverse S shapes, kind of flipped forward, kind of like a hook. You can go online and see really crazy pictures. And why bones matter. Our bones are alive and they're constantly healing. They're constantly developing or degrading, depending on our age. And they respond to stress. So it's really important to get outside and do some minor impact exercising, like hiking would help make your bones stronger. And then, and also like with the, all bones are obviously landmarks in the clinical arena, but the xiphoid process in particular is used all the time in CPR and radiology as a surgical landmark. And with bones, forensic scientists can determine things such as the time of death or how old they were, etc. And one of the things I thought was important is that things like the xiphoid process could appear as a tumor-like shadow on x-rays. So they're more than framework. They're the foundation of human motion, protection, and resilience. And that's it. Thank you for listening. They're my references.